So, have you ever wondered why a bee sting hurts so incredibly much, but if you just rub a little baking soda on it, it basically magically dulls the pain? Or why a really fiery stomachache is instantly calmed by a chalky tablet? Well, welcome to this explainer. Today, we are completely unpacking the chemistry that governs our daily lives, and we're focusing specifically on the invisible balancers of our world: acid, base, and salt.
We've got a lot of ground to cover, so here is our roadmap for today. First, we'll define acids and bases. Second, we're measuring their strength with the pH scale. Third, we'll look at the clash, neutralization reactions. Fourth, we'll dive into salts. And finally, we'll wrap up with everyday acid-base chemistry.
All right, let's jump right into part one, defining acids and bases, and looking at their core identities.
Let's start with what we can actually sense. Notice how your everyday physical experiences completely contrast the fundamental properties of these two things. Acids, like that lemon or the vinegar sitting in your pantry right now, they have a distinctly sour taste, right? And in a lab setting, they'll turn blue litmus paper red. Bases are basically the complete opposite. Stuff like soap or baking soda tastes bitter, they feel kind of soapy and slippery on your hands, and they turn red litmus paper blue.
But, what's actually happening on a molecular level here? Well, back in the late 1800s, the Arrhenius concept gave us a great foundational definition. It states that acids are substances that break apart to produce hydrogen ions, specifically hydronium, when they're dissolved in water. Bases, on the flip side, break apart to produce hydroxide ions in water. So the absolute crucial point to remember here is that dry chemicals really don't do much on their own. Water is the key. It's the necessary ingredient that unlocks these active ions so they can conduct electricity and react.
Fast forward a bit, and scientists broaden this with the Bronsted-Lowry concept. This one focuses entirely on the movement of protons, which are really just hydrogen ions. Under this definition, acids are proton donors, and bases are proton acceptors. I like to think of this like a microscopic game of catch. The acids are the enthusiastic pitchers, just throwing protons, and the bases are the catchers waiting to receive them. It's a beautifully simple dynamic, and it's literally the engine driving countless chemical reactions all around us.
Okay, moving right along to part two, measuring strength with the pH scale.
To actually figure out how strong these chemicals are, we use this awesome, colorful gradient. It runs all the way from highly acidic, down at 0, to highly alkaline or basic, all the way up at 14. The pH scale is literally just a direct measurement of the hydrogen ion concentration in a given solution. So the closer you get to 0, the stronger the acid. The closer you get to 14, the stronger the base.
And right in the dead center is the number 7. Pure, freshly distilled water sits exactly here. It's a perfectly neutral 7, which serves as the ultimate pivot point for all of these chemical reactions. It is completely neutral, neither acidic nor basic. It's honestly so fascinating to see how tangibly this maps out in our real physical world. Just look at how stomach acid sits way down at a highly acidic 1, while the baking soda sitting in your fridge rests pretty comfortably over on the basic side, right around an 8. We can map literally everything onto this scale. You've got the citric acid in a lemon down at a 2, all the way up to intense stuff like household bleach at a 13.
Which brings us to part three, the clash, also known as neutralization reactions.
Before these forces actually clash, we really need to understand strength at a molecular level. Strong acids and strong bases, they completely shatter into their individual ions when you mix them with water. They dissociate fully. Weak acids and bases, though, they only partially break apart, which leaves a lot of the original molecules completely intact. And this difference absolutely dictates how dramatic their eventual clash is going to be. So, when an acid and a base finally do meet, they undergo what we call a neutralization reaction. This step-by-step process is essentially a chemical peace treaty, where the acid and the base cancel out each other's extremes. First, they mix together. Then the hydrogen ions from the acid and the hydroxide ions from the base pair up to produce something entirely harmless, liquid water. Finally, whatever positive and negative ions are left over, they link up together to form a salt.
And that leads us right into part 4, salts, the chemical offspring.
You see, that chemical peace treaty produces a family that is way larger than just the salt shakers sitting on your dining table. Common salt, or sodium chloride, is actually just the base ingredient used to manufacture tons of other chemicals. From the baking soda that makes your morning pancakes super fluffy, to washing soda for cleaning glass, all the way to the plaster of Paris that doctors use to heal broken bones.
This whole relationship between acid, base, and salt yields some incredibly versatile compounds.
But wait, this brings up a fantastic question. You might logically assume that because they come from a neutralization reaction, all of these salts must sit at a perfectly neutral pH of 7, just like pure water. But is that actually true?
Actually, no. It turns out the offspring inherits the traits of the strongest parent. What that means is, if a strong acid reacts with a weak base, it's going to produce a salt that still leans slightly acidic, pulling a pH under 7. Conversely, if a weak acid reacts with a strong base, the resulting salt is going to be basic, with a pH over 7. You literally only get a perfectly neutral salt when a strong acid and a strong base go head-to-head completely evenly. Finally, let's wrap up with Part 5, Everyday Acid-Base Chemistry.
Let's take absolutely everything we've learned, pull it out of the laboratory beaker, and apply to our own bodies. Your digestion is a perfect 24/7 functioning chemical lab. Your stomach naturally produces hydrochloric acid to break down the proteins you eat. But when it overproduces, you get that awful, painful, burning sensation, right? Well, taking an acid introduces a mild base into the system. It acts as a chemical peacekeeper that neutralizes that excess acid, produces harmless salt and water, and totally calms the burn.
We also see this invisible battle happening constantly in defense and decay. Think about it. When a bee stings you, it is literally injecting you with a painful acid. No wonder it hurts. That is exactly why rubbing a mild base like baking soda on the sting brings immediate relief. Out in nature, if you ever accidentally brush up against the extremely acidic sting of a nettle plant, rubbing it with a basic dock plant leaf acts as a brilliant natural cure. And right inside your own mouth, bacteria are constantly feeding on sugars and producing acid. If your mouth's pH drops below a 5.5, your tooth enamel literally begins to dissolve and decay. That is precisely why you use a slightly basic toothpaste every day. You're neutralizing those mouth acids to save your teeth. We are all constantly managing pH levels literally just to survive.
But hey, it's not all about defense and decay. It is about delight, too. The sheer joy of eating a perfectly fluffy piece of cake. That is just an acid-base gas evolution reaction happening right inside your oven. When the baking soda in your cake batter gets heated up, it breaks down and releases carbon dioxide gas. Those little gas bubbles get trapped in the dough, which causes it to rise and become beautifully spongy. From the digestion of the food we eat, to the relief of a painful sting, to the baking of a delicious cake, we are all walking, talking chemical reactors. Now that you truly understand the invisible balancers of acids, bases, and salts, I highly challenge you to look at your everyday world through this fascinating lens of chemistry. So, what reaction will you notice next? Keep observing and keep learning.